Welcome back to Alternative AR here at AWE 2020. Next, I will be joined by Eric Chen. Eric Chen being CEO of Belus 3D. Many of you potentially very familiar with Eric and his work. He's considered a pioneer in the world of 360 video VR imaging and is named one of the 100 most influential scholars across graphics. Eric is here today to talk to us all about his journey in Belus 3D, the future, the past, present, and, all things VR imaging. Eric is, somebody that can really go into detail about companies specializing in 3D face scanning. And what I would like you all to do and really urge you to do is put as many questions as possible into the chat for our live Q&A towards the end of Eric's chat. The stage is Eric's.
Hi, my name is Eric Chen. I'm the CEO of Belus 3D. I'd like to thank you for joining the session. My talk is going to be talking about using mobile depth cameras to do 3D face scanning. Belus 3D is a company specialized in 3D face scanning. We've been doing this for 5 years. Let me share with you the technology that we have. When I talk about mobile depth camera, let me clarify what that means. If you have a more recent iPhone, such as iPhone 10 or above, you have a mobile depth camera that's built in, which Apple used to do Face ID. It's using structural light depth sensing technology. There are other mobile depth cameras out there, mostly using active stereo. They are usually separate detachable cameras, such as the Intel RealSense D series. That's an active stereo camera. Now, recently, Google Pixel 4 also introduced a depth camera that's using active stereo technology, which I will talk about. Now, Belus 3D, we have a new camera just came out this year. It's called ARC. It's also active stereo. There are other cameras out there using time of flight, which you are probably familiar with. The most prominent one would be the one from Microsoft Azure Kinect. For face scanning, we prefer to use structural light of active stereo, mainly because they are more accurate for close range, high resolution face scanning. So we're going to focus on those. I want to give you a teaser what the 3D face scanning quality will be like with one of those cameras. This is a model we created about 2 years ago using a previous generation of our depth camera called Belus 3D Face Camera Pro, which retail for $500. You can create a model like this with a 1/4 mm versus 4K texture map in about 40 seconds on an Android tablet. And that was 2 years ago. Now today, you can get a model with this quality using an iPhone 10 in about 10 seconds. So mobile depth sensing technology, like I mentioned, we're going to focus on structural light, which basically you got a camera seeing the projected pattern emitted from a laser projector, and they're usually using a dot projector because it's easier to manufacture, and the lights are usually infrared light because then it's not affected by the ambient light as much, and also it's not visible to human eyes. So to do depth sensing, usually what you do is that you got find the corresponding block between the dot pattern and the reflected pattern visible in the IR image. So by using triangulation of the corresponding block, we can determine the depth. Active stereo is very similar to structural light, but it adds an additional camera. So now instead of trying to find the corresponding blocks between a pattern and image, you are trying to find the corresponding blocks between left and right IR images. Now there are pros and cons of the two approaches, which I don't have time to get into the details. I would say that the structural light, Apple owns a lot of patent in this space. Active stereo is more like an open design, which is easier to manufacture too. The quality is comparable if you do it right. Okay, so let's talk about how we do 3D face scanning with this camera. So first, we need to capture the face from all different directions. Typically, you will move the camera around the face to try to scan from different directions. But you can also turn the head, which is equivalent. To get a good face scan, typically, we need to capture somewhere between 50 to 100 frames. Each frame will result in a 3D point cloud, which is basically the points captured from the depth cameras. And then we need to register all of them so that they are aligned, and we can stitch them to create a surface mesh. And after that, we will create a texture map, and each mesh vertex has a UV coordinate that in the texture map. And we can optionally, for face scanning, we can add 3D landmarks, which are feature points on your face. We can also turn the scan model into something with a fixed topology that makes it easier for animation. And finally, we can output the model in standard 3D formats such as OBJ, PLY, and so on. I'm going to get into more details in the following slides. So first, we talk about scanning. I mentioned that you can have an operator move around, but it's hard to do when you use an iPhone with a front-facing camera. So what we have created is a self-scanning process where the user will be asked to turn their head left and right. And the phone will guide the turning. We use the voice and haptic feedback. So as you reach one side, the feedback the phone will vibrate, so you know you're supposed to now turn to the other direction. During the scanning, we are tracking your face orientation and head pose. So the scan times depends on where you're going to do face only, which require only a left to right scan, or you want to do forehead, which will in addition add up and down scan. It will take anywhere up to from 15 to 20 seconds. So after that, we can construct the surface mesh from this. We start with the depth frames, which are what the depth camera sees. And by merging the 50 to 100 frames, we can create a pretty smooth surface mesh. We can remove the noise, we can fill in the holes and so on. But the depth frames are usually lower resolution than, say, the RGB frame. So we can incorporate the color frames, which are much higher resolution and have far more details, into the surface reconstruction process using technology called shading. By looking at the shading and shadowing properties of the surface, we can add additional details to the surface. So you can see it on the right side, we can see a lot more details there. And this whole process of merging all the frames and reconstructing the surface, it takes only about 5 seconds. So it's pretty amazing. Now that we have the surface mesh, the next step is to construct the texture map to add color. The surface mesh usually only has a small number of points. It could be up to 1 million points, but that's still pretty low res compared with what we can get from the high-res color frames. So what we do is that we have a separate texture map, in this case a 4K by 4K texture map, and then we have the UV coordinates of that we constructed from each mesh vertex is indexed to the texture map. That gives a much higher quality of the model than you would if we just have a color per vertex. In terms of texture mapping, you need to figure out a projection, which will basically flatten the 3D surface into a 2D image. Right? So in this case, there are many ways you can do that. The projection we use we try to minimize the face distortion, which means that we want the face still looks like your face, because the face is 3D. When you flatten it, it becomes 2D. So we try to minimize the distortion there. And the advantage of that is that now you can actually modify the face easily by editing the texture map. So here, for instance, if you want to do the virtual makeup, we can easily just modify the texture map without changing the 3D geometry at all. We can also optionally generate a normal map, which is a surface orientation map. So this is useful if you don't want to render all the polygons. You can have a lower polygon count, but use the normal map to add the details. And the texture map generation in our pipeline takes only about 2 seconds on iPhone. Okay, so now that we have the mesh, we have the texture map, we can then export it. Now, the surface reconstruction we do is that we actually construct it at very high resolution. But then when you want to export it, we can decide what kind of resolution you want to export at. So here we can export a low res one, which is only about 5,000 vertices, a medium one, 60,000, and all the way to full resolution, about 1 million vertices, which is what we compute at. So this is the choice that you can make based on what your applications are. Typically, for VR, AR, you probably don't need very high resolution, but for 3D printing, for medical application, people do need much higher resolution. For face scanning, obviously we have additional properties that is a human face. So it's important for us to understand what's in there. We can do facial and ear landmark detection from the color images and depth images. And then we can construct the landmarks in 3D and then map them to the scan model. So this is very useful if you want to say, I want to do virtual try-on. I need to know where the eyes are, where the ears are. I want to put glasses on it. The landmarks become very useful. So the scan model we have, every time we scan, we get different set of points because these are samples we get from the scan. So the topology and the number of points are not fixed. And that makes it difficult if you want to do animation, you want to do morphing, you want to rig the face. So what we can do is that after we have the scan, we can take a template model, which is a fixed topology, and fit it to scan model. Literally what we're doing is that we take the template model to format to match the geometry of the scan model. So by doing that, we create a new model that has a fixed topology. Every scan will have exactly the same number of points, and the points also correspond. So this makes it very easy to do animation and morphing and so on. So that kind of cover the whole 3D face scanning pipeline. Let me give you a jump up a little bit, talk about Better 3D's face scanning solution. So we have a fairly complete solution. As you can see that at the lowest level, we got our own 3D scanning hardware called Better 3D Arc that I will talk about in a moment. We also support iPhone, iPad Pro, which has built-in true depth camera. There may be other Android phones coming out that has depth camera, which we'll also support. And then in the middle layer, we got SDK, which interface with the depth camera and then provide high-level functions to construct 3D faces, from which the developers can create your own applications for whatever application that you have, such as eyewear, try-on, VR, AR, and so on. We also have now in App Store, one is called Face App, that's more for consumer, and then Dental Pro, which is for dental professionals. So talking about Better 3D Arc, this is a new camera system we are launching earlier in the year. We are about to ship it. So basically, it's a multi-camera system. We use a building block approach. So each individual camera is an active stereo depth camera, which you can see on the upper right of the slide. It has 2 IR sensors, 1 RGB sensors with a laser projector, which similar to the active stereo approach that I talk about. So each camera is an independent camera that can do depth sensing. But more interesting is that we can combine multiple cameras, up to 7 of them, to create a multi-camera system, which can be controlled by a single host PC to capture your face from all different directions. So this allows us to simultaneously do a face scanning without you turning your head or moving the camera around. And the capturing takes only a couple seconds. And then we can process all the capture frames to create a full head face scan. And then make it a lot easier, especially if you want to deploy in a kiosk in a more professional settings where the speed of capturing is important. And also the success ratio is higher because there's fewer variables in terms of how people turn their head and so on. It also has built-in lighting, so we can have a better control of the illumination. We have an SDK available, so this is basically a product we designed for developers to build their own applications on. Here's an example of a full head scan created in our system using 7 cameras. And this whole model took only about 30 seconds to create. Before I go, let me show you an application we built recently. So as you know, COVID-19, now people need to wear face masks. So we have very quickly used our face scanning technology to create an iPhone app that's a free app. Anybody can try it. That allows you to scan your face and then create a personalized mask frame that will fit your face perfectly. And then you can use that to provide a much better seal of your face mask, which is kind of loose fitting. And this will improve the effectiveness of the mask. So this is one example I want to share with you what you can do with 3D face scanning. So with that, I'd like to thank you for listening to the talk. I'll be happy to answer any questions.
Hey, Eric, pleasure to have you with us today. And, thanks for setting aside some time to give us a great insight into Belus 3D. I guess I'd like to open the questioning really with what inspired you to create Belus 3D?
Well, I've been doing 3D graphics all my career. And the difference right now is with the mobile camera, the ability to capture much higher resolution is night and day different than when I first started my career. So, I just couldn't pass on the opportunity to jump back in.
No, absolutely. And as you kind of run through the presentation and being something I'm highly passionate about myself, numerous, levels of adoption in numerous sectors and spaces spring to mind, whether it be gaming, retail, so on and so on. What industries are adopting this technology now? And I guess, how do you see that shifting over the years?
Well, when we first started, we weren't sure who's going to use it. There was some professional application we were exploring. I covered a couple like dental, eyewear. But now with COVID-19, we saw a lot of consumer application because you need a face mask. And one of the issues with face masks is that how do you seal them properly? And then, so we quickly adopted technology for creating customized face masks. But I mean, I think this is just the beginning of many new applications, because imagine that there are several hundred millions of people who in their hand with a very high quality 3D scanner there, right, which never happened before. So I'm sure that other applications are going to come around.
Absolutely. And myself, being somebody that, has an iPhone capable of doing so, it's very intriguing. I did download the app before I came to the call and it works amazing. So congratulations to yourself and the team. We did have a fantastic question from somebody, one of the attendees. Is Belus workflow round tipping the ingest and generation from the cloud, or does it stay on the device?
That's a very good question. So all the scanning is done in a mobile device. Now we offer the option to save to the cloud, so you can do sharing. You can also retrieve the model later on. We do have privacy policy there that we strictly follow. So the user has the option to remove the model anytime they want to. Now we also have the SDK. So the SDK allows developers to get the scan model and then do whatever they want to do within the app without uploading to our cloud.
Amazing. Okay, perfect. And I guess, you know, kind of throughout your journey, and, you know, obviously being a specialist across graphics and something we've obviously seen, you know, moving forward rapidly, especially in games over the last few years, you know, what has been your biggest, I suppose, challenge with the creation of this technology? I guess whether we're talking about facial animation, facial scanning, or we're talking about the mask itself, because I know, you know, you're talking about, I suppose, cloth and the simulation around actual clothes and material. It gets very complex. So yeah, you know, what has been the biggest challenge?
Well, you know, I'm actually a software engineer. I'm not a hardware guy. I never built any hardware before.
Sure.
So when I first got into doing the face scanning, I was stuck with some hardware, which is not really designed for close range scanning, because as you probably know, the first generation of Kinect and other similar cameras are designed mostly for tracking, for gesture input, UI, and so on. So, I mean, they designed for kind of video rate resolution. So the performance has to be high, but the quality is not necessarily high. So when we're going to do scanning, it's actually the opposite. We don't need very high frame rate. We need high quality, especially at close range. So one thing led to another. I decided that for us to really get the best result out of our software, we actually have to start from the ground up, building our own hardware. So that was a big challenge, because, you know, imagine somebody never did hardware before. We made tons of mistakes. And
Sure.
you know, I would run a lot of time just even describing some of it, but that was the biggest challenge there. But it turned out to be, you know, you really need both hardware and software integration to get the best out of it.
Amazing. And one more final question that we do have from the audience. Sorry, I'm just grabbing it here. It's quite small text. From a game and VR dev perspective, the workflow from mesh scan needs to go to retopology, fit to a mesh with blend shapes built in. Does Belus have a step-in SDK workflow that handles the retypo? What about blending the head for the mesh?
Yeah, so I kind of covered that. The retypo feature is not officially released yet. We do have technology to do that. So basically, we got a template model. We can then use it, retopologize the model. Problem is that it's usually specific to your application. So usually the single model template doesn't really work. We may have to open up so that we can take whatever model that you need. Once you fit it into a template, then the rest is easier, because now you have a fixed set of points that you can work with. Either you want to create blend shapes and so on. But the hard part is really the model fitting part.
Amazing. And sorry to, you know, I would love to chat all day, and of course, you know, obviously swiftly on to the next person, but it's been absolutely amazing to have you, and obviously extremely insightful for, I guess, what could move us towards some level of digital humanization, I guess, in a way, you know, where we can take that avatar or that face scan and I guess, you know, what industries will adopt that across, you know, numerous emerging or immersive technologies. So, you know, thanks so much. And again, you know, it's been a pleasure to have you here. And yeah, thank you so much.
Well, the pleasure is mine. I appreciate the time. Thank you.
Thank you. Thank you so much. Take care, Eric.